Welcome to this presentation on anti-windup control. We will show that saturation results in integral windup. We will demonstrate with the Lotus domino server problem. We will explain why this issue has to be resolved. Here is the transfer function of the IBM Lotus domino server problem. This is the transfer function between max users and number of remote procedure calls. We want to track steps with the rise time of 10 samples, overshoot with less than 10%. It is easy to see the good and bad parts for the denominator, and BG is 0.47, K is 1, it has 1 unit delay. It is naturally discrete time system, so TS is taken as 1, NR is 10. For this NR and this overshoot, we get this omega and rho. Here is phi CL, and here is the Aryabhata's identity that needs to be solved. And we demand the use of delta here so that we will have offset free tracking in a robust way. We solve the system. The solution is given by R1 S1 as given here, and it is easy to verify the following control law. RC is given here, SC is given here, and TC, and this is gamma. Here is the file that I used to simulate it, IBM underscore pp underscore sat.sce. This is the Scilab file. This program has several options. We will choose simulate without any saturation limits option in this file. Here is the option given, simulate without any saturation limits. After simulating, this file is to be executed to set the initial values for this XCOS code, which is stb underscore disk underscore sat dot xcos, and you have to load it from the directory in which this resides. And here is that XCOS file's screenshot. We get the thick dotted line for the plant output, and it reaches plus minus 1 as required. It reaches plus 1 here and minus 1 here as required. What are the other lines? We will see them shortly. Thick dotted line is the plant input, and you can see that the plant input exceeds 1. It goes to some number like 1.2 here and minus 1.2 here. And we are doing the simulation for 1000 intervals, and this switch occurs exactly at 500. Let's go to the previous figure. See that at 500 it starts going in the opposite direction, it becomes negative. So for the first 500, the reference signal says that y should be at plus 1. For the last 500, it says that it should be minus 1. So the input has to go to plus minus 1.2, plus here and minus here for offset free tracking. What if the input is constrained to a value of 1? Suppose it is not possible for the valve to supply this high input value. Suppose the valve can give only up to plus minus 1. If the constraint is there, what will happen? So that is typically indicated with the help of this saturation block. After some point, it becomes flat. Here is the value given by the controller. Notice that we are using the 2DOF controller. The controller says U is the control effort to be applied, and that comes on the x axis. and the y axis we have u set. Beyond some value the output becomes constant. So it saturates at that value. This is our plant, this is our reference signal, and this is our disturbance or noise, and plant output is given as y. We use the same Scilab file, but then now we choose the option simulate saturation, but do not use anti-windup control in this file. Simulate saturation, but do not use AWC. It's here. So in Scilab, when you fire this, you will get a window. You will have all these 4 options. You have to double click on this. And of course, the xcos file is the same. Xcos setup file also is the same. When you run them, you get this response. The constrained input results in thick continuous line. We are constraining it to 1. Although the plant requires a control effort of 1.2 as we saw earlier, because of the restriction it stays at 1. And more importantly, at n equals 500 it does not switch. It should switch here, but it does not switch, continues to be positive when it is supposed to be negative. What is the reason? We will see it in the next slide. In this slide, we will see the offset in output. It is supposed to be 1, but then there is an offset. There is a output here is indicated by the thick continuous line, and you can see that there is a gap here. Here is also an offset. The output never reaches set point, it always has an offset, and as a result, because there is an offset, the control law has an integrator which cranks up. It thinks that it is not working properly. So integrator will crank up if the error is non-zero. Error is non-zero, perpetually non-zero, so the integrator cranks up, and hence u reaches a very large value. So u sat does not switch at n equals 500, y also does not switch. U sat, the saturation value we saw in the previous slide, let's go back and see this. It didn't switch at 500, so as a result y also does not switch at 500. It continues to be positive even though it is supposed to be negative for this duration. This is the result of integrator cranking up. At 500 it should have become negative, but it doesn't happen. It has built up a very large value, and from there it has to decrease. So as I mentioned earlier, the non-zero offset results in controller output cranking up. Controller output remains positive beyond 500, in fact it changes only around 550 or so. Because it is positive, the u sat remains positive, and hence y also remains positive beyond 500. So this is a serious problem. One problem is that controller does not produce offset free tracking, that is the plant output does not reach the set point. More importantly, it is at a positive value when it is supposed to be negative, that is even more serious. We will conclude this video with these remarks. This problem is known as integral windup or integrator windup or reset windup. One solution is to stop cranking up when the actual control law that is implemented is different from the control law calculated by the controller. At that point we should remove the integral action. We also have an alternate solution using pole placement approach. We will explain this in the next video. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.